In terms of the climate benefits of GM crops to date, reduction in tillage is probably the most important thing by far. In terms of, in fact, if you think about the kinds of things that cause collapse of agricultural production systems, it's not about a little bit of pesticide use. It's excessive tillage of the soil and soil erosion that's really causes big problems. It's been estimated that around the world, this has also reduced the amount of CO2 being lost from the soil by about 100 million tons a year because of reducing tillage. It doesn't turn soil over so that carbon can oxidize and volatilize away. It's also been estimated there's about 9 million tons of CO2 that are saved every year because of reduced fuel consumption, because we can dash across the field at 30 kilometers an hour spraying a herbicide with a light rig instead of dragging steel through the ground to try to control weeds, which is energetically much more costly. And it's been estimated this is the equivalent of reduction of some 6.9 million cars per year in terms of the overall impact. So the impact is quite large. And I think when these GM crops were first introduced or considered, this was not something that people gave a lot of thought to in terms of what the overall impact would be. I can tell you when you go to places like the impact of this, if you went to a cotton farm in southern Georgia in the United States, as I did at the time it was introduced, you could tell what was going on in these fields because it was a non-Roundup ready cotton field. You could tell before doing any tests or asking the grower because you could look at the color of the runoff coming out of the field, and it was brown if it was a conventional field, and relatively clear if it was coming out of Roundup ready crop. You could almost tell without a road map which fields were which. And it led to the increase in adoption of Roundup ready cotton in Georgia alone increased from 20% to 80% in under 4 years, because the growers could see the benefits of weed control and appreciated what it meant to reducing erosion. My particular area of expertise and experience was in insecticide resistance in BT cotton crops, which essentially have a synthetic gene based on a plant gene, on a bacterial gene rather, to provide resistance to insect attack. And in Australia, this has led to something on the order of a 70 to 90% reduction in insecticide use, where essentially the insecticide treatments have been made are for non-caterpillar pests. And in China, the reduction has been about 75 to 80% by Chinese estimates, and that this has also created a reduction in pesticide poisonings in China on the order of 75 to 80%. And to put this in context, before BT cotton, when I went to China in 1996 at the invitation of the Chinese government to talk to them about how to manage resistance in their cotton pests, estimates we had independently in the West were that 400 to 1,000 people a year in China were dying from accidental exposure to cotton insecticides. Tens of thousands were probably suffering illness and morbidity. Essentially what BT cotton has done is it's greatly reduced the level of poisonings that are occurring. And I was able to go back to China and talk through interpreters to cotton growers in 2003, and they said it was one of the best things that happened to them. They were making more money on their cotton, and they or their families weren't sick. So this is a sort of benefit for, in China, literally about 5 million growers and families. In terms of the ones that, turning now to the crops that are in trials and what kinds of things they can do. Now I often hear people say these are theoretical crops, they don't exist. You'll hear anti-GM campaigners. I'm not going to talk about the ones that are still in the lab where people have got neat ideas. I'm talking about things that are actually in field trials now that in principle could be 5 to 10 years away from commercialization. These include nitrogen use efficiency, water use efficiency, and salinity. I won't talk too much about salinity, but I'll talk a lot about nitrogen use efficiency. And the focus on this was put by the New Scientist magazine a few years ago, where they noted that farming contributes more to global warming than all the world's cars, trains, ships, and planes put together. And the single biggest problem with farming is not carbon, but nitrogen. Although only a tiny proportion escapes in the atmosphere as nitrous oxide, it's from the nitrogen we apply, that's the important part because it's a potent greenhouse gas, estimated to be 270 to 300 times more important by weight than CO2. So if you start to look, people started looking at nitrogen efficiency some time ago, actually as an artifact of understanding basic plant physiological processes. And the interests include that, you know, with this given level of nitrogen application, you get higher yield, better insurance on yield, less fertilizer use, less runoff. And these were some of the early trials that showed, that just compared what happened with a control that doesn't have the nitrogen use efficiency gene compared to plants that do. There have been field trials run. These are from some of Alan Good's group in Canada, where they looked at canola, and they looked at genetically modified type compared to a wild type. And you can see if you were, it sort of yields on the order of 3 tons per hectare. You essentially get the same yield with a nitrogen use efficient crop on about 1/3 of the nitrogen use. Now, if on large scale, just looking at some of the biggest crops in the world, if we could reduce nitrogen use by even 1/4, much less 1/2, the impacts on a global scale in terms of environmental benefits would be enormous. And these are field trials that are already underway. The company that was working on this, Arcadia Biosciences, has largely licensed the technology to some of the big players in biotechnology and has decided itself to focus on rice production in China as a place to really work on nitrogen use. So the bottom line from this is, in principle, you get less fertilizer use. You get a lot less CO2 production from just the production of nitrogen fertilizer through the Haber-Bosch process, and all the energy that's required to transport to the field and drag it into the soil. In principle, right off the bat, you can get significant reductions in the amount of carbon emissions just from that. And on top of that, get less runoff and less nitrous oxide production just on scale of how much less you use. What about water use efficiency? These are some drought-tolerant corn trials in the field, where what you typically see is that with the water use efficiency gene, there's less curling of the leaves, and corn plants, when they're drought stressed, very typically have the leaves curl up. And you can even see this in terms of leaf temperature, that the ones that don't have the nitrogen use efficiency gene are relatively hotter compared to the ones that do, because they're respiring more efficiently and cooling more efficiently. And you can see the impact of yield at harvest, that essentially the variety that didn't have the water use efficiency gene had very little yield. The ones with the water use efficiency did a lot better. And it's a bit harder to see in this example in cotton, where it's also being trialed. But again, these are the ones that have the water use efficiency gene compared to the ones that don't. And just at the level of open bolls, you can see some sort of differences at harvest. Not quite as dramatic maybe as in the corn. Now, this is a complicated system. Working out just how to make water use efficiency work is not as straightforward as nitrogen use efficiency, because when water really matters to a plant varies depending on flowering, it's actually a much more complicated thing than just sort of jamming a gene in there and expecting to work. But it's still quite intriguing. I'll be really quick with one last example. In Tabletop Mountain in South Africa, there's something called the resurrection plant. And this has a particular resonance for me, because when I was an undergraduate at UC Davis, there was one of these in the courtyard in the botany building, and they let it dry down every summer, and then to really amuse all the kids, they take a beaker of water and pour onto it, and this thing that looked dead would restore within 24 hours. And it turns out that it does various things. It has protection in its cells by including sugars like trehalose and so forth that give it osmolyte protection. Well, people have been experimenting with this and putting it in plants as well. And these are some tomato plants generated a few years ago, where the tomato plants were grown to a certain stage, the water was withdrawn. This is what they look like a day after the water is added. That's what it looked like 4 days after water is added. What do we often have happen in Australia? We run toward the end of the cropping season. Grain crop hasn't really filled out yet. Rain stops. Then you get rain later when it doesn't do you any good. I mean, in principle, this technology could help protect yields under such circumstances. So to quickly sum up, if you think about the key issues in agriculture in terms of health and environmental sustainability, you want conservation of soil and water in terms of quality and quantity. You want to reduce energy use. You want to reduce persistent pesticides. You want to look to reduction of fertilizers, reduce production of toxins, various other kinds of pollutants. And you want to improve economic and social systems. And GM crops have already delivered on several of these, and it looks like they're well poised to deliver on others. Thank you very much.